Hi, my name is Hamza. I'm a research scientist at Google. Today, I will be presenting this joint work with my collaborators, Sai, Rishabh, Animesh, and Nina, titled Hark, a deep learning system for navigating privacy feedback at scale. As we all know, there have been significant efforts lately to improve the developer-to-user communication channel. One clear example is the data safety section on the Play Store, where users can see how their data is being used and shared. However, the reverse user-to-developer channel remains underexplored. In this work, we asked the question of how can we create a better user-to-developer channel to communicate privacy concerns. And we answered that question with Hark. Hark takes the set of reviews submitted on the Play Store as an input. These can be about any topic, not only about privacy. We built a fully automated pipeline that consumes these reviews and outputs and quantifies the top privacy themes. For example, here it says that the unneeded access is present in 546K reviews. The top fine-grained issue in that theme is the unneeded location access with 89K reviews. To illustrate this issue, Hark allows discovering high-quality reviews diversified across the emotions dimension, like angry reviews, confused reviews, etc. One might ask, why is the user-to-developer channel important? Previous works suggest that the developers who are made aware of privacy reviews tend to carry out related updates. In the permissions context, nudging developers results in reducing unnecessary permissions. It has been also shown that there is a correlation between low app ratings and negative privacy reviews, which can serve as a motivation for developers to act. Now we provide an overview of Hark's component in the following slide. Hark works in multiple stages. Given a set of reviews at the level of app, developer, or even the store category, we have a privacy classifier that finds the privacy feedback. The feedback is then fed into an issue generation model that produces fine-grained issues representing each review. Then, these issues are grouped into higher-level themes that are easily glanceable. To make it easy to navigate through the feedback, we have two additional models. The first is an emotions classifier that assigns one of 28 emotions to each review, allowing developers to filter data by emotions. We also have a feedback quality scoring model that surfaces the highest quality reviews to the top. We then can perform a variety of trend analyses on top of the outputs from these models. Here's an example of how reviews look like. They can be very informal and commonly have spelling errors. Our privacy classifier sifts through the data to extract the privacy reviews and exclude the non-privacy ones. Our issue generation model assigns each review one or more fine-grained issue tags. For example, unneeded contact access is assigned to the review saying, why does it need access to my contacts now? Next, issues are clustered into themes. Here we abstract the combination of hide photos, hide videos, and hide files into content hiding. All of this is done automatically without being restricted to a predetermined set of issues or themes. So we start by describing the privacy classifier. We want to differentiate between privacy and not privacy feedback, but the main challenge is that the data for this problem is severely imbalanced. Previous works estimate that reviews about privacy are less than 0.5% of the reviews. Now, some approaches try to mitigate this by searching via keywords, regular expressions, and labeling data that is surfaced. This leads to the model overfitting on the presence or absence of these expressions. Our approach is to use a natural language inference model for retrieving semantically relevant data to the privacy domain. We guide our retrieval with concepts selected from privacy taxonomy. The advantage of this is that it can generalize well beyond keywords. It can also achieve a higher coverage of a variety of privacy concepts. Now, as I mentioned, we leverage a well-known task in NLP, which is natural language inference. In this task, we are given a premise and a hypothesis, and we want to determine if the hypothesis is true, false, or undetermined given the premise. Let's take a generic example. Houston is freezing and dry right now. If my hypothesis is that the city is really humid now, there is a contradiction. If my hypothesis is that it's cold, then that's true. We say there's entailment. If my hypothesis is that it's crowded, then the verdict is neutral. There is nothing proving either way. Our idea is to use a generic model trained on analyzed datasets to sample data matching privacy hypotheses. Let's see how we do that. We started from a couple of well-known privacy taxonomies: Solov's taxonomy of privacy violations and Wang's and Kopsa's taxonomy of privacy-enhancing technologies. From each of these, we extracted the concepts that apply to the context of app reviews. We also added generic privacy concepts for general mentions of negative or positive privacy issues. Next, we came up with one or more hypotheses for each concept. The goal is not to be comprehensive, but to ensure that we have examples of each concept when we label data. For instance, for the concept use limitation, one hypothesis would be the data is being used for unexpected purposes. Finally, we apply this idea by checking where each hypothesis applies within a corpus of 9 million reviews. For example, these are two cases with high entailment score for the disclosure concept. Notice that neither of them has the word disclosure. The first review doesn't even share a single word with the hypothesis, but the entailment relationship is detected by this model. Our approach is to use the entailment score as a way to get a pseudo-balanced candidate set for data labeling. Reviews with high entailment scores for some hypotheses are potentially privacy-related. Those with low entailment score for all hypotheses are potentially not privacy. The candidate set is then passed to human annotators. We set up the task for manually annotating this data. Each data item was labeled by 5 crowdsourcing annotators who were provided with clear guidance on what to consider as privacy-related. Finally, this almost balanced data set is split into training and testing data for our privacy classifier training. We now move to the training part. We use the T5 model as a model of choice. It's a unified text-to-text model where the input and the output are always text strings. This has been used for classification, summarization, translation, etc., and has been leading the natural language understanding benchmarks recently. Since it is using the text-to-text paradigm, we also use it for other problems in this work. We apply it in the privacy case by taking inputs such as "it's always spying on me" with the word privacy as the target, as well as inputs like "it's always playing with me" with the word not privacy as the target. To evaluate our approach, we investigated 2 dimensions. First, we wanted to show the importance of better data sampling, so we compare models trained on our own data versus those trained on what we call the ICSI data, which is data sampled via regular expressions guided by a set of privacy concepts and created by Nima et. We also investigate the model choice. In addition to the T511 billion model, we evaluate the Roberta large model that is smaller than the T511B model, but still has been achieving strong results on various classification tasks. We additionally compare against an SVM model based on a bag of words in an attempt to reproduce the model used in a previous work. On this plot, we show the ROC curves for the various models when evaluated on the Hark test set. We can observe that the T511B model has 0.17 absolute increase in AUC when replacing ICSI data with Hark data. A similar trend is observed in the Roberta large model, indicating the importance of the data sampling strategy we adopted. We can also observe that the SVM model fails to learn the nuances of the problem and is limited due to relying on explicit n-graph. So deep learning models leverage transfer learning, and the larger the model, the better the results are with the same training data in our case. Now that we have narrowed down the feedback to the privacy ones, we move towards generating the user issues. We want to generate 1 or more issues per review. The main challenge is how can we generate issues that are not necessarily seen before, while still being concise, consistent, and fine-grained. Some previous approaches relied on classification. We categorize a review from a set of limited options. Other works relied on identifying the key phrases in the review and considering that to be the issue or the requirement. These approaches are limited since classifiers can only get one of the predetermined labels, and key phrases do not recur across reviews. Our approach is different. We take an abstractive generation approach. We developed a generative model that is trained to produce issues in the style of succinct labels that are either new or have been seen before. The advantage is that the outputs are consistently worded issues that recur across reviews. Moreover, it accounts for newly emerging issues. We formulate the task as text generation task in T5, the same model we use for the privacy classifier. We include the reviews text in the input, so it would be as you see it here. We include the list of issues we want in the target. Then we fine-tune the T5 model to generate such targets. You can find more details about evaluating this model in the paper. We briefly now describe the theme generation part. You might recall that we want to summarize the fine-grained issues into high-level themes. We won't go into details of the process in this talk. You can check them in the paper, but here's an overview. Given a set of issues in our corpus, we first perform a clustering of issues based on their embeddings. This gives us a set of issue clusters. To avoid the manual work of interpreting what these groups are about, we also have a theme title generation model that takes the most frequent issues per group and produces theme titles. Now, how do we get these theme titles? You might have guessed it by now, but we also use an abstractive title generation approach by combining a custom dataset with a T5 model. The custom dataset looks like this. We have a list of issues in the input, and we have the theme title as the target. Then we train the model on such a dataset and evaluate it against baselines via a comparative crowdsourcing experiment. So after building this pipeline, we applied it at scale. We applied our methodology to the largest dataset of Play Store reviews to date, including 626 million reviews coming from 1.3 million apps. With our privacy classifier, we find that around 6 million reviews were classified as privacy. Across these reviews, we identified more than 300 high-level themes with more than 1,000 reviews each. We conducted several types of analysis on this corpus. In this mosaic plot, we show the top 10 themes across the whole corpus, split by emotions. We can see that unneeded access is the top theme, with over 500,000 reviews. This is followed by generic privacy concerns and personal information privacy. You can also see interesting trends across emotions too. Users are mostly angry about the unneeded access. However, the theme content hiding is dominated by joy. The presence of positive emotions in these themes represents users that are expressing their content with the absence of privacy invading behavior sometimes. This aspect is typically underrepresented in previous work and can act as a positive reinforcement for developers. Next, we will drill down into the top fine-grained issues within the spying concerns theme. We can see a variety of aspects, such as general spying mentions, tracking, spying on spouse, spying camera detection, etc. It's surprising that some of these issues, such as spying on spouse or partner, get a lot of joyful emotions, and it would be interesting to delve deeper into them in future research. To further show how one can go into details about each issue, we will further zoom into the tracking app issue. Hark enables us to check the high-quality codes from this issue, diversified across emotions. Here, we just show 4 emotions, but you can see more examples in the paper with other emotions. The idea is that it's possible to build various ways of prioritizing issues on top of Hark via these filters that emotions classifiers provide. In summary, Hark is an end-to-end system for extracting and analyzing privacy reviews. We achieved 3 requirements that we aimed for: topical diversity, high coverage of privacy concepts, glanceability, developers can understand the gist of topics without having to read all the reviews, and navigability, developers get the high-level picture and can delve deeper into issues on demand. Thanks again for your attention and for organizers for creating the opportunity to present remotely for those who are hindered from coming by the US visa system. And finally, a shout out that our team is hiring. Feel free to reach out to my colleagues Sai and Animesh, who are available in person, to answer your questions about the paper too. Thanks.
All right, so first I want to apologize. I unfortunately swapped the content of the last two papers. So this was obviously not about differential privacy and homomorphic encryption. It was about using NLP to categorize different sentiments and language related to privacy. So you take, well, you can ask questions. Any questions?
Hello. Thanks for the talk. One thing I had in mind was how did you, so it seems like there's 3 levels of hierarchies, the reviews, the issues, I think you call it, and then the high level theme. Why 3 and not 4 or 2? What was the,
So we essentially wanted to balance out the amount of time or the information that we share with the developers, and also give them the details that they would like to do. We felt like this was the best option that was possible. Like initially we thought we can just have an issues to reviews as just a 2-level thing. But then the number of issues that we were generating were too many to handle. And even if you remember one of the slide, we had like about 500 or so themes in total that we had identified across the full data set. So if you pick a particular app, an app might have like 30 or 40 themes, which was easy to scan into, and also if they wished, they could dive deeper into it. So there was like a fine balance between how many we show the developer, and also at the same time give them the option to dive deeper if needed.
so it seems like the number of highest level themes per app was kind of the determiner of how many.
Exactly, yeah.
Got it. All right, thanks.
So I have a question. So are there situations where different users can, for example, express the same thing using different language, and then this ends up being mapped to different categories, and so at the end of the day, you don't actually get the right counting? So if you want to prioritize things, it doesn't quite work out.
Yeah, that can definitely happen, but that problem is partly eradicated where we group the issues into themes. Probably you might not realize this, in one of the spying themes that we had seen, like the fine-grained issues were slightly different. Like one is like spying spouse, one other is general spying, where there could be an overlap of the topic, but when we do the aggregation at the issue level, this problem would diminish to a large extent. So we get to count them accurately as much as possible.
I see. And then one other question is, you seem to be using a lot of techniques that are common in the NLP literature, such as summarization, and finding emotions. Did you have to do adjustments to any of those techniques, or you can just use the black box mechanisms themselves and combine them?
So we had to fine-tune the models to our use case, because if you were to use them as is out of the box, they don't apply well to the data set that we are working with. So we saw a lot of noise creeping into the system. So we had to fine-tune these models to our use case, so that's as to get better results. Of course, if we were to use them out of the box, instead of getting something like 90% AUC, we might get like 70%, which is still good. But fine-tuning might give us the best results possible.
Okay, thank you so much. Let's thank the authors once again.
You.